So now we've seen a couple of ways of identifying whether numbers are prime and sort of generating examples. So let's turn to some questions about the distribution of primes. So let me say what I mean by this. By this, I basically mean how many prime numbers are there? But by distribution, I mean that we'll be giving a couple of different answers to this question in a couple different levels of detail. So, question, how many primes are there? So, the first answer, the simplest answer that we can make is there are infinitely many. So let's prove this quickly. So we're going to prove it by contradiction. So we're going to write down, suppose that there are only finitely many. We write down a list of all of them. And then we write down a number that is not divisible by any of them. So it must have a prime factor not in our list. And there will be some practice problems and homework problems to make variations on this argument. But let's go through it. So proceed by contradiction. And actually, let me just, off the top of my head, make some remarks about proof writing. If you want to show there's infinitely many primes, maybe working by contradiction is a reasonable thing to try, because that gives you something that you can write down concretely, which is a finite list of prime numbers. So if we want to proceed by contradiction, what we can do is so suppose there are finitely many primes, and then we can write them all down, essentially. So not explicitly, but let's give them names so that we can work with them. Then, essentially what we can do is use these explicit, not super explicit, but like use these concrete list of primes to write down a concrete number that somehow does not come from these primes. So consider P1 times P2 ... times Pn plus 1. So what are the relevant facts about this number? It is not divisible by any number pi, but we know it must be divisible by some prime. Maybe we want to be super precise, but it is greater than 1 because it's this thing plus 1, and this thing, we know that, for example, there are a couple of primes at least, so this is not 0. So it's greater than 1, so it must have some prime factor. And this is the contradiction. Which completes the proof. So this is a contradiction, right? Because we have this number, which must have a prime factor, but it is not divisible by any of the primes in our list. That is the contradiction. So there is the first answer to our question, how many primes are there? The answer is there are infinitely many. But we can refine our question a little bit by asking what percentage of numbers are prime, or what proportion. Or maybe another way of saying this is how many, let me close this window. How many numbers less than or equal to some fixed number x are prime? So let's give some other examples for context before we answer this question. How many even numbers are there less than or equal to x? Well, we can say that about half of numbers are even, right? Because they alternate even and odd. So about half of numbers are even. And one way we can make this rigorous is by saying the number of even numbers at most x is about 1/2 x. So as x varies, this always gives us a pretty good estimate for the number of even numbers up to x. The number of square numbers up to x is about, can we figure out what this is? So the idea is that n squared is at most x is going to happen exactly when n is at most square root x. So the perfect squares less than x correspond pretty much with the numbers, well, they correspond exactly with the numbers up to root x. So the number of perfect squares up to x is about square root x. So you can see that this is a little bit more refined than the answer we gave before, because you can think of this as saying there's infinitely many of both, but somehow there are still more even numbers than perfect squares. Right, because essentially this is going to grow faster than this. If you look at x equals 100, for example, this thing is 50 and this thing is only 10. Or if you go even further and look at 10,000, this is 5,000 and this is only 100. So there are lots more even numbers than there are perfect squares in this sense. So this is, in contrast to the cardinality sense. The cardinality of even numbers is equal to the cardinality of perfect squares. They have the same cardinality. But in this more refined sense of how frequently do they occur in the integers, there are more even numbers. So let's now answer this question for the primes. The answer is called the prime number theorem. And it says the number of primes less than or equal to x is about x divided by ln x. So this, of course, is the natural logarithm. And what kind of thing is this telling us? Let's give a concrete example of this. How many primes up to 10,000? Well, the answer, of course, is about 10,000 divided by natural log of 10,000. And if you compute this out, it is about 1,086. So the true number, I mean, you can just count the number of primes less than 10,000. That's not too big of a number. The true number is 1,229. So you can see that, it's not exactly a bullseye, but it's probably better than your own wild guess was going to be. Well, I shouldn't say that. Maybe you could have guessed better. But personally, I find it quite hard to just guess off the top of my head how many primes are less than 10,000. And this is getting you sort of well within 20%. You're about 15% off, which is not bad. So let me say not bad. So one more comment about the prime number theorem is that, the fact that there are infinitely many primes, we proved just now, it was not too bad. The fact that the number of primes is about x over natural log x is quite a lot more difficult. So this is not something we can just prove in a couple of minutes. This is a big, fairly big, difficult theorem. So let's finish this part with one more refinement. Let me make one more comment real quick, just to relate this back to the context. I don't know how obvious this is to any of you, but what's true is that the number of primes is in between these two numbers. So x over natural log x is going to grow slower than this, but faster than this. So there are more primes than there are perfect squares, but less primes than there are even numbers. But okay, one more refinement. So refine further. So we have this, I'm saying a little bit informally, the number of primes is about x over natural log x. How good is this estimate? And this is one of the most famous problems in mathematics. The Riemann hypothesis. Can be considered a version of this question. There's many things you could mean by how good is this estimate. Some of them are easier or harder to prove. But the Riemann hypothesis, which is one of the Millennium Prize problems and is one of the most sort of famous mathematical problems, you can think of it as being a statement about how good is this estimate of the number of primes.